Okay, so this is a dynamic programming question, and it's about the change giving problem. So we've got a currency where the denominations of coin are 5, 4 and 1, and we're being asked to give change of amount 8. And the problem we have to solve is what is the minimum number of coins required to give this change, and we need to compute it using dynamic programming. So to use dynamic programming, we need to write down a recurrence and a base case, and then we use that to complete our table, which is going to store the final solution and also all of the simpler solutions that we use to compute the final solution. And we're going to do this bottom up. Okay, so in the end, what we're going to build is a table. So with I and coins of I. And we're going to go from 0 all the way up to the desired amount, 8. Okay, so the question is, what do we put in coins of I? And we need to write that down as a recurrence. So let's maybe start by thinking about a base case. So the simplest case would be if I'm asked to give change of 0, I can do that with 0 coins. Now, another possible base case that you might think about would be coins of 1, 4 or 5, because I can obviously do that with 1 coin. And they would be fine, they would be reasonable base cases, but you don't actually need them. We'll end up getting back to this simplest base case of 0 anyway. So let's try and write down a recurrence. So we need to express the solution for coins of I in terms of some simpler problems, so coins of some smaller values than I. Now this is the hard part of the problem, and it requires a bit of thought for how you might come up with this recurrence. So the intuition that you require is, let's think about if I knew the solution for coins of I minus 1, so if I knew the minimum number of coins required to give change of I minus 1, then I could give change of I with 1 more coin by just giving a coin of value 1. Similarly, if I knew the minimum number of coins required to give change of I minus 4, I could also give change of I by just giving 1 more coin, by giving a coin of value 4. And finally, same goes for I minus 5. So if I knew the solution to any of those 3, then I could give the change that I require, change of I, by just giving 1 more coin. So either giving a 1 or a 4 or a 5, depending on how far away I am from that. Okay, so the question is, which of those 3 should I choose? Well, I'm trying to give change with the minimum number of coins possible, so I should take the min of these 3 things, and then I'm going to have to add 1 more coin. So let's just say again what this is telling us. So this is a recurrence that says to give change of I need to find out how to give change of I minus the value of my 3 possible coins, so minus 1, 4 or 5. Once I've solved those simpler problems, I take the minimum, whichever one can be done in the fewest number of coins, and then I add 1 to that because I just need to give 1 more coin to give change of I. Right, now we've got our recurrence and a base case, we can complete the table bottom up. So let's start filling it in. So let's fill in the base case first. So to give change of 0, I need 0 coins. Now we're going to use the recurrence for the first time, and we can see we have a bit of a problem now. To solve coins of 1, we're going to be making reference to coins of I minus 1. Well, that's okay. But I minus 4 and I minus 5 are not defined. So we need to make our recurrence a little bit more complicated. I'm not going to write it all out here, but we will only consider, of the three options, we'll only consider those that actually exist, i.e. those that are defined within our table. Okay, so let's start filling it in. So for change of 1, we're only going to consider the top option, I minus 1. So we're going to look here. We can see there's a 0 there, so we add 1 to it, and that's what we put in the next position in the table. Same goes here, so we can look at position I minus 1. There's a 1 there, so we add 1 to it, put 2 in our table. So let's just think what this is saying. It's saying to give change of 2, I can do that in a minimum of 2 coins, and obviously that's by giving 2 1s. Okay, same again, so we look back 1. To give change of 3, I can do that in 3 coins. So, so far this has not been very interesting because in the recurrence we only had one of the options. Now for the first time we have 2 options, so I can look at I minus 1, I can also look at I minus 4. So I'm going to take the minimum of those 2, which is obviously the 0, and add 1 to it. So what this is saying is to give change of 4, I can do that in 1 coin, and that's by obviously just giving a 4. Right, we're now ready to use the whole recurrence, so I can consider I minus 1, I minus 4, and I minus 5. And I'm going to take the minimum of those 3, which is obviously 0, and add 1 to it. So again, I'm saying I can give change of 5 in 1 coin, and I do that by just giving a coin of value 5. Okay, for 6, let's look back 1, 4, and 5. So I have 2 equal minimums here. So I minus 5 has a 1 in it, and I minus 1 has a 1 in it. So this is not surprising. This just corresponds to the 2 options of giving a 1 and then a 5, or a 5 and then a 1 to give change of 6. So either way, I can do it in a minimum of 2 coins. So it doesn't matter which of the 2 I choose. Okay, so for 7, again, we look back 1, 4, and 5. Again, I have 2 equal minimums, which is a 2, so I add 1 to it to give me a 3. So this corresponds to giving a 5 and 2 1s, and I could do that in any order. And finally, we're ready to compute the solution to the original problem. So I want to give change of 8. So I look back 1, I look back 4, and I look back 5. Okay, so the minimum here is 1. I add 1 more coin to that, and I can give change of 8 in 2 coins, and that corresponds to giving a 4 and then a 4. Okay, so we've solved the final problem, which was how do I give a change of 8, but notice that we've also solved all of the smaller problems, so all i's less than 8 as well. And notice that we did this bottom up, and we were using memoization to store the partial solutions in the table, so we never replicated any work. Any problem that we solved, we stored the answer to it, and then we reused it when we needed it again.